This morning, Remi Rhodes, to talk about the 2D random Kähler geometry.
Thank you. So I would like to thank the organizers. So they aren't there, but for the invitation. And so also I would like to apologize for the last for not being there for the last two speakers, Joshua and Tunan, because I have to rush to the train station after my talk. So sorry for that. So so today I want to present a project that we started to think about a few years ago, with following discussions with Steven Zeldich and Semyon Klevtsov. Well, it's about the validity of a, well, say a folklore statement saying that the random geometry in 2D quantum gravity is described by UV conformal field theory. So the fact is that this statement is certainly true when you couple quantum gravity with conformal matter fields, and we try to understand what can happen if we go beyond this framework. So of course today I have no general statement about that. So I will present a model that arises when you just slightly move away from conformal symmetry. So you can think of it as in a given context of a near critical random geometry, admitting the fact that well, UV CFT could be the critical regime. Okay, so this will be a three-level talks. At first, in the first part of my talk, I want to explain the motivation. So this will be a macroscopic scale of explanation. I just want to give you the motivation. There are no mathematical statements in this part of the talk, okay? So I just want to explain a situation where the model I will present may arise, and how it can lead you to consider a given path integral. Then in the second part of my talk, I want I will explain okay, so well, you don't see maybe the second part, but in the second part I will explain a bit more this path integral and how you can construct a random geometry out of it. And in the last part, the third part of my talk, I want to explain a bit further how you can construct this path integral. So, well, just to recap a bit, the question in at least Euclidean 2D quantum gravity. So the question is that where is the pointer? Okay, pointer. So the question is that you want to construct. So you take a Riemannian manifold M, and you want to construct. Well, you consider all the possible metrics, the Riemannian metrics that you can put on M. So for me, just to be clear, a metric is a collection of inner products on the tangent spaces of my manifolds. It's not a distance, because there are some talks where a distance function is called a metric. So just to be clear, it's a collection of inner products on a given manifold. So you want to construct a formal integral where the integration variable is a metric, a Riemannian metric on the manifold, and you want to construct a measure dg, which is more or less the L2 metric on the set of all Riemannian metrics. This is exactly the structure Julien described in this talk. And so the thing is that when you are in a finite dimension, when you have a metric on a manifold, the prescription to construct the volume form is clear. Okay, but in the infinite dimensional framework, well, this measure does not make sense mathematically, and you want a way to understand this measure dg. And what is this z here? This z here is just the partition function of a model of statistical physics. In this context, it's called a matter field. So this is the function. Actually, this is the function of the metric. Okay, and you want to construct this measure. And if it has a finite mass, so it gives you a probability measure on the set of metrics, and you can get out of this a random G, a random metric, okay? So the thing is that if you want to give a sense to this object, the shape of this function here, this partition function, will greatly influence the shape of the measure dg. Okay. So what is known is that this is called the Polyakov DDK and that. Well, it started in the 80s. It says that when this partition function here is the partition function of a conformal field theory, then the random metric, if you can construct this measure here, the random metric G or the measure dg is related in some way to the Liouville conformal field theory. Okay. So this is a statement because when you have a metric, you can construct the volume form with the help of determinants. This is defined as a determinant, and you can play with determinants here in infinite dimension to show that actually the random metric is indeed described by Liouville conformal field theory, but this is a formal statement. This is a formal statement in infinite dimension. So if you are more involved into rigorous proofs, there are these two ways that you can use in math to make sense of this statement. First of all, you can discretize this measure, and a correct way to do this, maybe there are other ways, but a correct way to discretize this dg measure is in terms of random planar maps. And to show that this random planar maps converge to this Liouville CFT, this is a program that Scott, Jason, and Bertrand and others have developed. Okay, so and it is in the context when the conformal matter field here is the partition function of CFT. Okay, so there may be another way. If you want to construct a measure, you can certainly construct a dynamic. This natural dynamic, and this natural dynamic is the gradient flow, and you want to consider the stochastic gradient flow, and study the invariant measure of this stochastic gradient flow. Okay, and if you can show that the invariant measure of this stochastic gradient flow is a given measure, this is certainly a way of giving sense to this dg measure here. Okay, so you have two approaches to make this statement correct, and the second part here is the content of Julien's talk last week. Okay, so just a word to recall. Just roughly the idea in Polyakov DDK and that. So my talk will be to consider here the partition function of some matter field, which is not as general as it could be, but just slightly moves away from conformal symmetries. Okay, and see what happens for the dg measure. Okay, so just a few words about the Polyakov DDK and that. So the idea is to use arguments to show that you can have a good idea of the law of the random metric G if you look at what is called the Weyl anomaly, or sometimes the Polyakov's anomaly formula. Well, you look at the way the partition function of your matter fields react to what's called background change of metric. So you have a metric G, and you apply, you modify it, you multiply it by exponential of some smooth function. This is the action of the Weyl group, and you look at the way the partition function react to this background change of metrics, and actually you can show that this ratio here, the log of this ratio, is proportional to what's called the Liouville functional. Okay, so at this point of the talk, I don't want to write. I don't need to write what is the Liouville functional, but more or less, what the upshot here is that this quantity, if you compute the ratio, it gives you the Liouville functional, and so the argument says that if the random geometry is certainly described by a path integral involving the Liouville functional. Okay. So as an example, you can look at the partition function of the GFF. So more or less, it's a Gaussian integral in infinite dimension. You can give sense to this Gaussian integral, and it's related to the determinant of the Laplacian. Okay, well, normalized in the good way. This is well, we have seen this determinant of Laplacian in many talks by Lin or Julien and many others. Okay, so this is an example of matter fields which satisfy this anomaly formula. Okay, with the Cm here is equal to 1. So now we can try to consider the simplest model of massive matter. Okay, so this is just more or less this is a Gaussian free field, and you add a mass. Okay, here you add a mass, and you have a linear term in the action. So and you want to understand the coupling of this massive matter field to quantum gravity. And actually, I have no idea how to answer this question. It's well, it's a bit too complicated. But what you can do, certainly, is to, well, let's try to understand what happens if we send the mass very close to 0. Okay, so you can define a model. Well, what I call the m equals 0 model is it's to remove divergences. Well, when you send m to 0, it's important to know that there are divergences in this integral, and if you remove them, you can define a limiting partition function. You may think that it does not depend on the mass, but the way you remove divergences keeps track of the fact that you had mass in the beginning. Okay, so this is more or less m equals 0 GFF, and this is not the GFF, the conformally invariant GFF. Okay, so it defines a partition function of some given matter field, and if you want to apply the DDK scaling, now you compute the reaction of your partition function under the Weil group, and you see that now the ratio is a sum of two terms. There is a Liouville functional appearing in the ratio, and there is another term which is called the Mabuchi K-energy. Okay, so well, this is a very simplified presentation of a series of works by Bilal, Ferrari, and Klevtsov and Steven Seldich. And actually, the framework is a bit more general, but this is just a simplified version of their model. Okay, so if you believe the DDK in that, certainly the coupling of quantum gravity to this model should give you a path integral, which involves two action functionals. First of all, the Liouville functional, and second, the Mabuchi K-energy. Okay. So
Can I just ask a naive question, just to make sure that so I mean here the mass is the mass that you put in front of the field, so it's not the same as if you would just change the Green's function and putting a mass, right? So what you're saying is that this massive guy is not absolutely continuous with respect to the one without mass, even locally, right?
No, it's okay. There are two things in this path integral.
Sort of like
yeah, okay. There are two things. If you have a path integral, there are two things. There is this is integral, so there is the mass of the integral, and there is the law of the field. The law of the field is certainly the massive free field, okay, the one you know. But the mass here keeps track of the way you remove divergences and so on. Okay, so there are two different things. If you just look at the probabilistic object, this is the same as you know. But the mass, you have to compute it, take care of the computations. Okay, I want just to be maybe a bit clearer, I won't look at the law of this object. I just want to look at the mass. Here, this is the total mass of my path integral. Okay, is it clear? Or? Okay, no, maybe not. Well, this is if you. Okay, if you don't like this presentation, just think that you can define a function on matrix, I say lateral function on matrix, which satisfies this anomaly. Okay, and you can just take it for granted. This is a weight that you can put on matrix. Okay, and you want to understand the coupling of this object, no matter where it comes from, with quantum gravity. Okay, so what I want to explain now is how to construct a path integral involving both uv and k energy. Okay, so if you want to make a mathematical statement out of this, well, two conjectures, rough conjectures. I don't want to enter into too many details. You can look at random planar maps. So this is a usual prescription. You have you consider the set of all triangulation with n faces on your manifold, and you pick your triangulation at random among the triangulations with n faces according to the weight of your function of matrix on matrix that it gives to the proof to the matrix that you have on the triangulation. Okay, so this is a way of sampling at random your triangulation, and you want to understand the scaling limit of the metric that you have on your triangulation when the number of faces goes to infinity. And second option, you can look at the stochastic gradient flow too. So the flow is here given. The flow here is given by these two terms here. Well, this is the term that you had in Julian stock. Here, this is the isotropic noise on M, and here you had another term corresponding to this new potential, and this is this new term here is given by the Ricci potential. Okay, so this gives you another flow, and the invariant measure for this flow is the path integral I want to describe. Okay, and this is if you are geometer, this is some mixed version of the Ricci flow for this part here, and here this is the Kähler Ricci flow. So it's a mixed version of both of them. Okay, so this is two mathematical statements. I'm not sure they are doable right now, but maybe checking that this is the right invariant measure for this model, maybe. But okay, this is just to have a rough idea of what I want to construct. Okay, so now overview. I want to present the path integral at a mesoscopic scale. So, well, in a
Can you go back to your
yes,
slide?
sure. Two slides. This one. This one.
Yes, this one. So it's really an expansion in terms of the genus you had?
No. The manifold is fixed.
No. How that you have a... Yeah, but you...
H.
This one, yes.
So the manifold M is fixed, so it has a genus, and the Weil anomaly makes the genus appear in the. But this is a Weil anomaly which depends on the genus.
So what is omega?
This is the conformal factor of the metric. So you just study the dependence of this ratio in terms of, say, the conformal factor. Okay. Is it okay? Okay, and this is not a small expansion in the mass. This is an exact computation.
No.
And actually, what they did, these four guys, is to compute in a more general framework the mass expansion. So they did that for the Ising model, massive Ising model, and the massive scalar field. Okay. Well, this is the two simplest model you can make this computation. Okay. So, the title of my slide. I mean, the question is what is a random geometry? I put natural, but okay, natural has no meaning. Just for me, at least, I want to explain my view on the topic. Okay. So, in geometry, if you do a classical geometry, the basic objects you want to look at are the manifolds with uniformized curvature. Okay, this is a way of classifying manifolds, and generally, this is not a clear statement, but generally they can be found by solving variational problems. So you have a functional, and if you are able to compute the minimum of this functional, you will get your manifold with uniformized curvature. Okay, so if you are a probabilist, well, what you want to consider is not the minimum of this functional. You want to construct an integration measure over a functional space. Okay, so this is what we call a path integral, and you want to construct a path integral. So this is a measure on the functional space. Here, more or less, this is the Lebesgue measure, if you want, on the space of function in this space. and you want to put a weight in front of it, the exponential of minus your functional. Okay, this is the way for me what is a random geometry. Okay, so I will explain this procedure for two functionals. So for the Liouville functional here, and then when the S is the sum of the Liouville functional and the Mabuchik energy. Okay, so for the Liouville functional, how it shows up in random geometry. So you are given a 2D manifold, and you want to uniformize. So you are given a metric on your manifold. It has not necessarily a uniformized curvature, and the thing is that you want to find your uniformized metric in the conformal class of G0, the metric you have, and so you parameterize some metrics by looking at those G which are conformal to G0. So you have an unknown function omega here, and you want to find the correct omega, the good omega, such that this new metric G has uniformized curvature. Okay? So how do you solve this problem? So this is an old story. Vincent gave a word yesterday about that, but okay, it's not too bad to recall how it goes. So now you are given some fixed. I'm given some fixed parameter gamma and mu. At this part of the proof, gamma is not necessary. Just to be coherent with the remaining part of my talk. So because I can swallow the gamma here in the mu. Okay. So this is just a superfluous parameter. So I add this new gamma here, and if I want to find the correct omega such that the metric G has uniformized curvature, you can, well, this is certainly a critical point of this functional here. This is a simple computation. And so this functional is called the Liouville functional, and I want to keep it on the blackboard. So it's one. And you integrate over the manifold. I'm not sure. Well, there is a 4 pi. Okay, and well, what will be important for the following is that the value of this parameter q here is given in terms of gamma by the relation q is equal to 2 over gamma. So this is, here I will gather the classical action. This is the action you use in a geometry. And q okay. So now, so this is a way to find metrics with uniformized curvature in 2 dimensions. And now, in what is I want to just give a very rough look into Kähler geometry. So you are. So I'm still in 2D, but Kähler geometry makes sense in a higher dimension. But just to have a rough picture, so you have a manifold equipped with a metric G0, and you still want to find a metric with uniformized curvature. So instead of parameterizing your metrics with conformal factors, you want another way of parameterizing your metrics. So this will lead you to other equation to solve to get your uniformized metric. Okay, so this way you want to parameterize your metrics in terms of the Kähler potential. So the Kähler potential is this function phi here, and to get your phi, so you have this. You consider a new metric G, which is conformal to G0, and the conformal factor is omega, and so you solve this equation here. Well, the unknown is the function phi. Okay, so recall that omega depends on phi, and phi depends on omega. This is just a two-way representation of phi and omega. So maybe I will keep this relation here. And this guy here is the Kähler potential. of G equal. Okay. So why should you care about this new definition? It's because actually using the Liouville functional is not appropriate in a higher dimension, and this is a working on Kähler manifolds. It's a further constraint on the manifold, and actually it turns out that if you cannot find in higher dimension, it's way difficult. It's way more difficult to find a matrix with constant Ricci curvature, and the framework of Kähler manifolds has been successful in the recent years. So now there is a full classification of Kähler manifolds with a series of work starting from the 70s with Obeniao, and then Chan Donaldson for classifying all these manifolds. Okay. So I don't want to discuss any further the case of higher dimensions. So I just want to now introduce the Mabuchi K-energy. So recall that you have a metric G, which is conformal to G0, and the conformal factor is omega. So you can define the the Kähler potential, phi, and the Mabuchi K-energy is this functional here, okay, in which you have the Kähler potential and the omega. But keep in mind that phi depends on omega, omega depends on phi through this relation. I could write everything in terms of omega or everything in terms of phi, but the more compact form is this one, okay? Is it clear at this stage? Okay, so now I write what I call the classical Mabuchi K-energy. So minus
What happens for h equal 1?
for
H equal 1?
yeah, for h equals 1, this functional simplifies drastically because you don't. So you don't have this is called the kinetic term, and all the kinetic term disappear. You are just left with the entropic term. Okay, so the case h is equal to 1 is a bit specific, but not only. Just let me finish to write this functional. And there is a 2 here. And furthermore, there is an important here. Of course, when h is equal to 1, this guy disappears. But you see also that depending on the genus, if the genus is higher than 2, this changes the sign, or if you on the sphere. So if you're on the sphere, this functional is no more convex, and this is why Donaldson and Jensen. It's why it takes so long. It took so long to classify the Kähler manifolds on manifolds with positive curvature. Okay, this is because this term changes its sign and it's no more convex. Okay, but in a genus higher than 2, this is the good sign, and well, this is a nice function for me. And this will be important in the last part of my talk, because we only construct this path integral on hyperbolic surfaces, because this time make the analysis much simpler. Okay? So if you look at this functional and you look for the critical points, you again find a matrix with uniformized curvature. Okay? So now, how do you construct the Liouville CFT out of this Liouville functional? So this is just a rough slide. So more or less, now you want to construct the path integral. Okay. So as I said, you want to construct a measure on the space of functions. So this is the measure, and I will denote with a bracket the average with respect to this measure with bracket and subscript L. Okay, so this is formally this is a path integral where you have this exponential weight which is given by the quantum Liouville functional. So this is more or less the same as this functional here, except that in the quantum case you have an extra parameter here which is the +2 over gamma. Okay, this are renormalization effects to give sense to this path integral, and it modifies the value of Q. Okay, so now there has been a few talks about the construction of this path integral. I will recall the definition in the last part of my talk. Just I want you to have a rough idea of this definition. And okay, so how do you recover a random geometry out of this path integral? So this path integral describes a random function phi, okay? And you consider a random metric you have a fixed metric, deterministic metric on your manifold. You consider a random conformal factor, which is exponential of gamma phi. Recall that phi is not random, provided that this measure has finite mass, okay? If this measure, the Liouville measure, has finite mass, it defines a probability measure if you renormalize correctly your expectations. So once you have a probability measure on the space of functions, it gives you a random phi, so you can define a random metric this way. I'm a bit vague here because defining a random metric is not is not direct because the field phi is very rough, but this is the idea, okay? So actually, as it turns out, that's what I was saying, phi is not fairly defined function, so it's not clear how to make sense directly of this expression. But you can look at observables of this metric, like the volume form, okay? And the volume form is you integrate this guy here on given sets. So you can do this by using Gaussian multiplicative chaos theory. You may also want to construct a distance function out of this. So it's a way more difficult story, but you can try to do so. And this is what Jason, Bertrand, Scott are trying to do for all values of. So eventually for all values of gamma, but well, as I said, the source of difficulty here is that this field phi is not smooth. Okay. Okay. Question on this? Okay, and well, what I will be interested in is the conformal anomaly of this measure on the space of function. So if I take if I look at the expectation value of this measure, and so recall that this path integral depends on the background metric. So you are given a metric, and given this metric, you construct a path integral, okay? And this path integral depends on the metric. So you want to know how this path integral depends on the metric. So for this, you consider another metric G, which is conformal to G0, and you look at the Weil anomaly of your path integral, and you can show that indeed this path integral has the expected Weil anomaly. I mean that it's log proportional to the Liouville action. Okay. Well, here I put a 0, meaning that this is SL of mu, and the Weil anomaly is for mu equal to 0. Okay. So this is a a standard conformal anomaly for CFTs. Okay. And the value of CL is 1 plus 6q squared, and this is the central charge of Liouville theory. Okay, so why should you care about this functional relation? It's because you can obtain a great deal of information on your theory, starting from this just simple symmetry. That you can, out of this relation, you can, first of all, you can obtain PDEs for your theory that you can use to solve entirely the theory. Okay, so this is what Guillaume told you about the BPC equations and the DOS formula. Okay, I don't want to enter into many details, but you can extract a lot of information out of this relation. It gives you also the conjectures with quantum gravity models like the random planar maps or the flow of your of the stochastic gradient flow. And what I'm interested in is constructing a path integral with a further Mabuchi term here. Okay, so this is now what I want to explain. So, I'm still considering a manifold M. Now, H will be the genus. I'm given a fixed metric G0, and I want to consider this path integral, which involves both the Liouville functional here and the quantum Mabuchi action computed on a metric which is at least formally conformal to G0, which is the Liouville metric. Okay. So recall that if you just look at this term here, this is the path integral for the Liouville CFT. Okay, it defines a random metric, more or less. As I said, it defines a random metric exponential of gamma phi G0, where phi is random, and you can try to compute the Mabuchi functional on this metric. Okay, so as I said, the metric is not redefined, but all I need to compute to get the Mabuchi energy computed on the Liouville metric is actually quantities that can be defined correctly. Okay, it does not involve the distance, for instance, or objects that are too difficult to handle. Okay, so this quantum Mabuchi K energy is this functional here, and just look at this term here. Okay, if you compare with the classical action for Mabuchi, you have again a quantum correction. Okay, the values of the parameters have to be modified in order to renormalize this path integral. Okay, so again, this term here, it differs from the classical framework because of renormalization effects. Okay. Well, this is what I want this is what we constructed. And so the statement, as I said, is that if the genus of the manifold is larger than 2, so this is because of the kinetic term you asked me, Bertrand. This is why we consider only hyperbolic surfaces. Here, when gamma is between 0 and 1, so here this is a technical restriction. You know that we can define the Liouville conformal field theory for gamma between 0 and 2, but there are technical restrictions that we'll explain a bit later. So here we do not cover the whole range of parameters. And for some coupling constant beta, which is again restricted to some ranges of parameters, but this restriction here is not technical. This is a topological obstruction. In the same way as the Gauss-Bonnet theorem is an obstruction on the manifolds, you cannot construct a metric with given curvature and a given volume, except if it satisfies Gauss-Bonnet. Here, this is a statement of the same nature. Okay. So this path integral exists and it has finite mass. So if it has finite mass, you can get out of it a random geometry in the same way as I explained before. Okay. So you have a random metric here, but this time the law of the phi is given by this path integral here. Okay. So well, now we have to check that we have the right Weil anomaly. So we change. So we have a path integral again, which depends on the metric, the background metric on which you constructed your path integral, and you want to study the effect of changing the background metrics. So we can show that we have the expected Weil anomaly. So the Weil anomaly is a sum of the Mabuchi, the classical Mabuchi term and the Liouville action. Okay. So we
classical meaning without the one.
Okay. Okay. There is the Q. I should have written here. Gamma over 2. This is for classical. This is for quantum. The Q here, and here. The 2 is for classical, and the 2 divided by 1 minus gamma square over 4 is for the quantum. Okay, but the Weil anomaly are expected to be classical. This is standard. Okay. Okay, and second, so if you have a path integral, as I said, you have a random metric. You can try to compute the volume of this metric. So you integrate this guy on the manifold. It gives you a random variable. and you can compute the law of this random variable. You can show that it has a gamma law with parameter S and mu, and in physics S is called the string susceptibility, and we have an exact expression for the string susceptibility, simple expression, but it was an open question in physics because they have developed quite a different approach, and so the question of having this string susceptibility was open, but when physicists don't have access to this exact form, they perform what they call a loop expansion, and actually we can show that we have checked that this expression here reproduces exactly the loop expansion by physicists. So, so again, with this Weil anomaly here, you can connect to the random model, the models that I have described in the beginning of my talk. So the stochastic gradient flow or this model on the random planar maps. And there is something funny with this path integral, is that, well, if you have a quantum field theory, well, a local quantum field theory, there is a statement in physics, in mathematical physics, that says that if you have a path integral which is local, local means that your path integral has this form. Okay. So you integrate over the manifold something which depends. So you integrate over the phi, and when say that the action is local, when you have an integral over the manifolds of some functional which only depends on the field at a given point, and the successive derivative of the field, okay, gx and so on. Okay, this is what's called the local path integral. Okay, and if you have a local path integral which is globally conformally invariant, this means that your theory is invariant under Möbius transformation, then it is a conformal field theory. Okay, so when you have a local action, global invariance is equivalent to local conformal invariance. By local, I mean conformal word identities. Okay, and this path integral actually is globally conformally invariant, but is not a CFT. Okay, this is because the action is not local because of the Mabuchi term here. If you look at the Mabuchi action, you have the Kähler potential entering this functional, and the Kähler potential is non-local in the field, okay? Because the field is omega, and if you solve this equation, the potential here is the integral of the green function over the whole manifold. So it's not a local term. This is why this is I mean, a bit intriguing. You have a QFT which has global conformal invariance and which is not a CFT. So global conformal invariance is important for being a good candidate, say, for scaling limit of random planar maps or something. Okay. So, so now, how do you construct this path integral? I mean, I want to get to the point. So, in my talk, well, I will consider for me G0 is a GFF on the manifold. So you have a manifold with a given metric G0. X G0 is just a GFF with a vanishing mean in the G0 metric. Okay. So this means that the green function of capital G, the green function of your Gaussian free field, is just the green function of this problem. Okay. Well, you can show this is, for instance, what Julien did. Well, this is something classical. It lives in a Sobolev space with a negative power. And if you want to construct a path integral, the first observation is that this gradient term, the action, is given by expectation law of this GFF. Well, the important thing here is that if you integrate over constant function, okay, the gradient vanishes. So you have, if you look at just a restriction of your path integral on constant function, this is the Lebesgue measure. This is why you have the C here, which stands for integration over Lebesgue measure. Okay, and also this path integral has a metric dependent constant. I will skip it in the following because it does not play a role in what I want to discuss. Okay, so first you have to interpret this gradient term as an expectation of GFF. So now, so just I recall that how you construct the volume of this random metric. So here you have the volume form on the manifold. You want to integrate exponential of the GFF. So this is a Gaussian multiplicative chaos, and this is the standard procedure. You regularize a bit the field with a scale parameter epsilon, and then you send the epsilon to 0. Okay, you introduce this epsilon in order to regularize the singularity of the green function. And if you renormalize your stuff correctly, you get a nicely defined random measure on your manifold, okay, which is a Gaussian multiplicative chaos on the manifold. Okay, and this is, I will call it G, calligraphic G, for Gaussian multiplicative chaos. Okay. Okay, so now the definition of the Liouville expectation, the Liouville measure on the space of all functions. Well, the terminology for me, the Liouville measure is this functional integral over the space of all functions. Okay, this is the definition, the probabilistic definition of the path integral of the Liouville path integral on the space of all functions. So here you have your the total mass of your Gaussian multiplicative chaos on the manifold. Here you have this DC, the Lebesgue measure over the variable C, which came from the GFF. Here, this is just a generic functional f that you apply to your field, and this term here comes from the curvature term in the action, in the Liouville action. Okay, and as your metric G0 is supposed to be uniformized in my talk, this term is constant, so. And it has vanishing mean in the metric G0, so it cancels out just to give this exponential of something times C. Okay, so I'm a bit vague at this point, but this is the definition of the Liouville function. Okay, so so now I want to plug into this expression. I want to plug the Mabuchi-Kähler energy of the Liouville metric. So I want to add this new exponential term of minus beta times the quantum Mabuchi-Kähler energy of the Liouville metric. So this is exactly this expression, except that 2 is replaced by 2 divided by over 4. And phi is the Kähler potential of the Liouville metric. So the Kähler potential of the Liouville metric is just this guy. So here you have a Gaussian multiplicative chaos that you integrate with respect to the Lebesgue measure, the green function. So more or less the green function, this is a log singularity. This measure here, you can show that it has Hölder regularity. So this guy here perfectly makes sense. And the difficult term to handle is the entropic term here, okay? So this term, if you want to make sense of it, you have to introduce what we call the derivative GMC. So we call that, well, this is this expression here so this more or less corresponds to conformal factor times exponential of conformal factor. So here, conformal factor times exponential of conformal factor, except that you have to renormalize this quantity to give it a proper sense, okay? So this is what you call D, calligraphic G for derivative, okay? Because you can obtain this expression by differentiating with respect to gamma the standard Gaussian multiplicative chaos. Okay, so you have to introduce this quantity on the manifold, and so now the crucial point is that you want to show that this random variable here has exponential moments. Why? Because this term, as I said, I have chosen age so that this term has a good sign. So exponential of minus a positive random variable has obviously exponential moments. So this guy is not a problem in the Mabuchi action. This guy disappears if the manifold is uniformized. So these two terms are not very difficult to handle, at least on hyperbolic surfaces, because this guy has a good sign and this guy is 0. So it's even better. So the difficult term is this one here, and this is exactly the one I wrote here. Okay, so you have to show that this guy has exponential moments. And so if you want to show that this guy has exponential moments, so you have to show that this guy here is not too negative, and this guy here is not too small. Okay. So so you need two results on DGMC and GMC. First of all, you have to evaluate the tails of the derivative Gaussian multiplicative chaos. So we show that at least we can, well, at least it has a sub-Gaussian tails. on the left. And the second result we need is that, so this guy is not too small. So we have a small deviation result for Gaussian multiplicative chaos. So let me first comment this term here. Well, there is something that could be misleading, because more or less formally you integrate exponential gamma x over the manifold. Okay. So formally, you want to say that, okay, it's not too difficult to see that this guy, to control the left tail of this guy, okay, because the function x exponential f is bounded from below, okay, so it shouldn't be too difficult to evaluate the left tails of this guy. But recall that the definition here, if you think so, you overlook renormalization by variance, okay? Because here you are subtracting minus infinity to your random variable, so it's not quite obvious to see to evaluate the left tails, and this is a standard problem in at least two-dimensional quantum field theory. There are in the literature all the p-phi theory, when the potential is not the p-phi theory is when the potential is not an exponential but a polynomial of the field, okay, polynomial of the field. And for all this polynomial, the method was by Nelson, and it uses hypercontractivity methods to control the Ornstein-Uhlenbeck semigroup associated to this interaction terms. But here, why hypercontractivity? Because when you have a polynomial, you live in a fixed Wiener chaos. Okay, so you can use all the technology of Wiener chaos and hypercontractivity and so on. But here, when you have as soon as you have an exponential, you don't live in a fixed Wiener chaos. Okay, so controlling the tails requires other arguments. And actually, what we do, we control this, because if you want to establish Gaussian tails, when the field is very high, it won't contribute obviously to the left tail of the random variable. So only the values of the field which are at least negative will give you the left tails. So we just control this martingale by another one where we suppress the large values of the field, and then we use Gaussian concentration methods. And the second comment I want to make is for the sharp deviation, what I call sharp, the small deviation result we have. If you compare with the literature, so there has been a lot of people working on the small deviation of chaos, and if you look at their results, so by Bertrand, by Scott, there was Mika Nicolae, so Nina Holden, well, there are a lot of results about small deviation of Gaussian multiplicative chaos, and what they proved is that usually a Gaussian multiplicative chaos has log normal tails. Okay, so why do we have such an exponent here, which is much smaller than their result? Is because when you have generally speaking, when you have a Gaussian multiplicative chaos, you expect their tail to be correct. Okay, so this is a log normal tail. Okay, or let's say log normal. Okay, this is because actually what dominates the tail here is the mean value of the field. Okay, so actually what contributes in this integral here is just exponential of gamma integral of the field over the manifold. Okay, so this is why you have a sub-Gaussian tail, log normal tail. But if you subtract the mean of the field, gamma integral of the field over the manifold, exponential of all of this. So you subtract the mean of the field, and you look at the small deviation. Then you remove this first order contribution, and then you want to look at the second order terms. Okay, and the second order terms is what we found here. Okay, and if you recall my definition of the field we use is the GFF with vanishing mean in the G0 metric. So it has indeed a vanishing mean. This is why we have this very small left tail. Very small small deviation. Okay. So this is how we prove that this guy here is has exponential moments, and so we've proved that this path integral has indeed a finite mass. Okay. So I think I stop here. Yes.
So just a naive question. I mean, what is it that suggests that a priori, if you're trying to formulate your path integral with a massive GFF, this has anything to do with Kähler?
If the mass is fixed, no, okay. So maybe first I go to the slide. If the mass is fixed, obviously, frankly, I have no idea. Well, okay. If the mass is fixed here, I have no idea. Okay. Okay. So if you don't know how to handle this situation, well, the first thing you want to do is, okay, let's perform an asymptotic expansion when m goes to 0. So you try, and what you see is that, well, the first terms are computable. But if you are asking for an intuition of why the Mabuchi action shows up, I have no idea. Okay, you make the computation, and this is very simple computation. Actually, you can show that for this model, this is just the exponential of the Polyakov action. So this is double integral of curvature, green function times curvature again. And just compute the Weyl anomaly. It's very simple. But for instance, if you are asking me for the second order perturbative term, then it will be no idea either. This could be a further understanding of going away from criticality. You can try to add successively no path integral of the perturbative terms, and I have no idea of the shape of the second order term.
So from the physical point of view, you view this as relevant because there's a massive GFF to begin with, or because it ends up with a Kähler potential?
Sorry, the end of...
You view this as sort of a relevant model because you start with the massive GFF and you can analyze it, or because really the end goal is to get the Kähler potential? What is the...
Well, you are asking for something natural. Okay, for me, what is not...
Next.
Sorry?
For the next situation.
Yes. Why it is natural? Okay, it depends. Of course, if I have any functional showing, well, so first of all, what is very nice is to have an exact relation, okay? Because it's not something that we perform after quantizing, okay? This is an exact computation here. For instance, the problem could be, okay, if you look at here, okay, the argument could be, well, okay, let's first quantize this massive matter field with mass m, which is positive and given. Okay. Then you say, well, you perturb when m goes to 0 and you find Kähler. This could be a problem because you have in the beginning no idea of what this quantized integral is. Okay. So here, this is an exact result. Okay. You can quantize with this model here. This is not. This is an interversion of limits. Okay. So first, you have this model. It is well defined for fixed. For fixed value of Q. It's well defined. It has the correct Mabuchi energy. Second convincing argument is that if you look at the stochastic gradient flow here, this is the well. Okay. If you like geometry, well, you are certainly convinced that the Ricci flow is important. And second step, that the Kähler Ricci flow is important. Okay. Well, if you are okay, these are two important flows in geometry. Okay, and this is the mixed version of them. Okay, so it's natural. You can ask also for well, this is a Seldich obsession. It's related to a deeper question, but you suppress the this the contribution from Ricci here, and you just look at the stochastic Kähler flow, and it should correspond to a path integral, which only involves a pure Mabuchi action. Okay, so so the question is, well, it's also very natural because here, well, there are many questions you can ask for this model. Here, just look at that. Okay, we all look at the GG measure. I mean, the L2 matrix on the set of metrics. Okay. Well, it's written in every paper on 2D quantum gravity. Let's take the L2 metric on the set of metrics. But actually, there is no physical prescription for choosing this metric. Okay. And for instance, something which is as natural as this metric is the Mabuchi metric on the set of Kähler potentials. So this is another structure on the for which quantum gravity makes sense. Okay? And if you want to quantize this way this functional integral over the set of metrics, you have to look at the Kähler-Ricci flow on the set of Kähler potential. And because of this, I erased it. But because of this argument of locality, the conjecture is that the invariant measure for the Kähler-Ricci flow should be again Liouville conformal field theory. But I have no idea how to prove this conjecture. But this is the, I mean, at least there is an argument for this conjecture. Okay, but so is it relevant? Why is this model relevant? Why is Liouville field theory relevant? I mean, some physicists say, well, matter is massive, so all your conformal field theory, I don't care. Okay, so question. At least there are universal objects involved in the game, so it's probably a bit relevant.
Do you have a way to view your object as first defining it in the universal cover somehow, and then reproject so that somehow you're, I mean, that there is a way to understand basically your additional Mabuchi thing as some sort of having something to do with that conditioning on the subspace where things are nicely correlated.
What do you have in mind? In some kind of Kähler potential on the set of metrics, or why?
Well, I mean, I mean, once you are in the universal cover, then you can try to okay, I don't know.
The universal cover of the
Now
manifold.
it's also semi-triangle.
No.
That is a natural.
Maybe, no, I have no idea. No, I don't have.
Do you think it's interesting or doable to look at when your manifold has boundaries?
When your manifold is?
Has boundaries.
Yeah, it should make sense, but we are not at this stage of the computation. So with the boundary, there are a lot of many more problems. First of all, you have to compute all the functional geometric functionals. First step, it's a lot of computation, but first step, and then if you want to compute the exponential moments, well, this was when you define the objects, the Liouville field theory on the disk, there are a lot of things happening on the boundary, and the analysis is way more difficult to define the theory than on the sphere, for instance. And at this stage here, for defining Mabuchi, I'm not sure we can handle this for the time being. So with the boundary, well, there are some technical things to check.
Thank you.